In this video, we're going to talk about the change in entropy and how to calculate that and how it's related to a reaction and which way a reaction is going to go. So let me get rid of the calculator here. That's the first thing. Okay, so it turns out that change in entropy, which is symbolized with a delta S, okay? So delta, remember, means change, and S is entropy, and this means standard. Okay, we're only going to deal with standard conditions, so you're just going to see this S up here. And so if you notice that this reaction looks very, or excuse me, this formula looks awfully familiar. Well, it is analogous to the enthalpy formula, and so that's kind of neat. So if you kind of know how to use the enthalpy formula, this formula can is used in exactly the same way. Okay, and so you can predict the sign of entropy based on how many moles of gas are on one side versus another. Okay, and so if we look, if we have more moles of gas on the reactant side, the side of the sign of the entropy, the randomness is the change in randomness is going to be negative. If you have less moles of gas on the reactant side, the sign of the entropy is going to be positive, which means it's going to get more random. Okay, negative means less random, positive means more random. Okay. Also, there is a sign convention like with enthalpy, but in this case, the signs are a little bit switched around. If you have a positive delta S, that means the reaction is going to favor the products. Again, it's not spontaneous. Okay, spontaneous is a different measure, but if it's a positive delta S, that means it is product favored. It's more likely to go to the product side of the reaction. This happens because the second law of thermodynamics says that the entropy of the universe is always increasing. So if the randomness is increasing because of a reaction, that means it's more likely to go toward the products than stay as the reactants. And so a negative and change in entropy means that the reactants are more random than the product, so there's no reason for it to go to the product. So anyways, it's a lot, but let's kind of apply this thing. Okay, so let's go here and go here and go here and go here. Okay, so it says calculate the entropy changes for the following process. Okay, so there are two processes here, and I know some of you out there are like, well, where am I going to get the delta S for any of these things, or the S for these things? Well, it's super straightforward. That table of thermodynamic data is going to have enthalpy or entropies of these compounds. So I happen to have one here, and what I'm going to do is I am going to transfer this to my notepad. That way I can do the math there. So there's our reaction. That's ethanol, liquid ethanol, and gaseous ethanol. And I went to my table of thermodynamic data and I looked up this. Okay. And just so you know, again, you just find a table. There's one in the back of the book. Let's see. So this one, it's usually arranged by element, and so this avoids any sort of organic compound, so I guess that's a little bit different. So, but you go to the back of your book and you find this. Okay, so how do we calculate this? Well, before we calculate it, one of the things that I like to do is have an idea of what's going to happen. So is this guy is a liquid, and it's going from a liquid to a solid. So is it going to get more or less random? Which one has a more, which one is more random? Well, the gas is more random. So it's going from a small random to high random, or middle random because it's a liquid, to a high random, which is a gas. So you can go and you can say, well, then the delta S, the change in entropy, should be positive, okay? Because there's a mole of gas over here and there's no mole of gas over here. Gases are so much more entropic or random that all we have to do is compare the number of moles. This is of gas. 1 mole of gas here, no moles of gas here. It's going to be a positive delta S. But let's calculate delta S. Delta S equals the summation of S naught products minus the summation of S naught reactants. Okay, now this reaction is a little bit easier because there's only one product and one reactant, but nonetheless, let's see, what's the S naught of the products? Okay, there's 1, the coefficient is 1, and the product is 282.7, and then that's it, minus products minus the reactants. There's 1 mole of reactant times 160.7, and so that's products times reactants. The mechanics of doing this math are just like the mechanics of enthalpy. Okay, so I'm going to bring up my calculator and I'm going to then do this, okay? So I'm going to go, and I know it's going to look weird, but okay, I'm going to go 1 times 282.7. You don't have to do the 1 times that. That's fine. And so there's our reactants. I'm doing everything to the nth degree here because I got killed when I was in college doing this. So that's that. And now this 1 times, so this is going to be minus 160.7. Okay, so what's 282.7 minus 160.7? Okay, and so that's going to be 122. So the delta S for this, delta S equals, and that's the standard delta S, equals 122, and keep it, the units on this is in joules. It's not in kilojoules, but it's in joules. Okay, now, what did we predict the sign was going to be? The sign was going to be positive. Okay, was the sign positive? Yep, it got definitely more random by a little bit. 122 joules, just so you know, is a little bit. I mean, that's not a ton, but it's not a teeny tiny amount. So that's pretty decent. So let's look at the next problem. So now for the second one, let me get rid of my calculator here. For the second sample, we have the formation of ammonia. Okay, now this isn't a formation reaction, it's just N2 plus H2. Now again, we can predict the sign. How many moles of gas are on the reactant side? The moles of gas here, there's 4. How many are on the product side? 2. So which side is more random? The reactant side have way more moles of gas than the product side. So the sign of the delta H, the delta S in this case, should be negative because it's going to go from 4 moles of gas down to 2. So it should lose randomness. Okay, so let's look at the problem and see what we get. So, okay. So again, I look up these values in the table of thermodynamic values, and we get that. Okay, so delta S naught equals the summation of S naught products minus the summation of S naught reactants. Okay, so this is going to equal, so the products, there's 2 moles times its S naught, 192.77, minus the reactants, so it's 1 times 191.56, plus, that's what summation means, plus 3 times 130.7. Okay, so now I'm going to do some math. Okay, 2 times 192.77. So when I do that, I get, let me see if I can get that to focus a little bit better. Okay. Woo! Come on. How about if I do that? Look. Yay. Okay. So this becomes 385.54 minus, now this is 191.56, 191.56 plus 3 times 130.7. And when I do that, I get 583.66. And I am super crazy because I take this, and so I get the answer there, and I get the answer there. And now I can do the next step of math. I'd rather not let the math get in my way. My college professor just killed me on this. Actually, I'm the one that made the mistakes, and so because I didn't do it slowly enough, I'm the one that ended up getting wrecked. Okay, but, well, whatever. 285.54 minus 583.66, and we get an answer of negative 198.12 joules. Okay, now that's what we predicted our sign was going to be. So this is how we this is how we calculate entropy, and this is how we can verify what we think the entropy of a reaction is going to be based on the number of moles of gas.